So this is the basic idea with double integrals. Again, I want to make that mesh finer and finer and finer. I don't want to slice x up into 4 pieces or 5 pieces or 6 pieces. I want to slice it up into 100, a million, a trillion, a billion, on and on to infinity number of slices. Which means that I would be accounting for each and every, right? It'd be like if I went out there with a popsicle stick and I was like, oh, this tall here, this tall here, right? But I can't do that in reality for the snow that's happening there. But I can do that if I had a function for how much snow fell in the general area. So, brings us to example 2. I'm looking to find the volume beneath the surface, and you guys have a nice picture of it there. And above the XY plane, over the rectangle, so it's the same sort of setup, only instead of going, 300 or so miles one way and 400 or 300 or so miles the other way, I'm just looking at something much more simple. 2 to 2. So I'm looking at a 2 by 2 rectangle. The snow, you can see this nice little cone shape. That's the shape of the snow. So it's like I'm looking at just a little 2 by 2 foot region on my roof, and I'm asking, okay, I wonder how much snow is really in there. So to do this, we're going to use the double integral. From the setup that we have, if you turn your front page notes sideways for some reason, you'll see that it should be equal to the double integral of the region f x y dA. So this begs the question, okay, what is this double region going to look like? Well, you guys want to slice it by the x's first or slice it by y first? Sure, we can slice it by the x's first. So that would be dx. So we're slicing this up into a grid based on the x's. How far do I let that slicing grid go? 0 to 2. But then I got to slice it by the y's. Where do I let the y slicing start and stop? Again, 0 to 2. And what gives me the height of the snow? That's my z function. Right? Z is the function. In this case, the region I'm provided by is 16 minus x squared minus 2y squared. That will give me the height of the snow. Now, where I'm going to be calling on you guys to assist me some today is that my Calc 2 integrals are not made what they're supposed to be, so we're going to go through these together. But most of them won't be too bad. So we're going to integrate the inside first. So we're going to put that dy integral, put it out of our minds for a second. And I'm just saying, what is the integral of 16 minus x squared minus 2y squared with respect to dx? This is a definite integral, so I'm going to need to evaluate it. When I evaluate 16, what is the integral of 16 with respect to x? 16x. When I evaluate x squared with respect to x? Yep. And then 2y squared. He is right. I'm going to go ahead, even though I know it breaks every tradition, I'm going to write it as 2y squared x. Because I'm still thinking of y as a constant right now in my mind. So I'm going to evaluate this. Do you guys use this notation? Okay. dy. Now, luckily, when I plug in 0, boom, 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 nada, right? This is why we love the number 0. So it's all going to go away. So now when I evaluate this from 2 to 0, I'm just looking at the integral from 0 to 2 of 16 times 2 minus 2 cubed over 2, sorry, over 3, minus 2y squared times 2y. This is equal to 0 to 2, 32, minus 2 to 2 is 4, 2 is 8. Yes, I know I can combine these, but I'm too lazy for that. So this is 32y minus 8/3 y minus 4y cubed over 3, evaluated from 0 to 2. Or as I'm burning through this at a decent pace, have I left anyone behind yet? No shame, right? We're a no man left behind kind of unit right now. So now I'm ready to plug in my 2. Pull out your calculator, punch that in, you'll get 48. Questions? Okay. Can I erase? Everyone caught up?
So when we type the integral with respect to x, the dx,
Uh-huh. Right, so it would be, so if, now that I can erase, I can really prove this to you. So what I'm saying is, right, like I said, just put these two integrals and this dy out of your mind, because we're just looking to integrate this right now, where y is considered to be a constant.
we
Yes.
basically take the integral of the function dx, put those in parentheses, then we take that answer and put that then integrate that as y.
Yep, you're really just doing this back to back. Take the derivative with respect to x, take that answer, take the derivative with respect to y. Like I said, really, I feel like compared to what you guys have been doing, we kind of lucked out. Tonight's not that bad. I mean, obviously, we're going to see that I can put some crazy integrals right here, and that makes just the pure integration itself hard. But if you can get behind the idea that I'm just going to build a grid, and I'm finding the area for each grid, the volume of snow in each grid, then the basic concept of what I'm doing here with these double integrals isn't too bad. In fact, yeah, and here's the thing: if you're like, he keeps saying it's not that bad, but it really is bad. I don't get what he's saying. Don't feel bad. Let me know. This is like the one. Why I'm saying this isn't that bad is because this is like the one thing I really remember from Calc 3, and it's because once you understand this one, it's kind of like understanding what the derivative is. You know, all the lights go off. You're like, oh, I see what's been happening all along. So. Point in case, tonight's big theory. Fubini's theorem says, well, let me throw some nice math notation at you. If I have a region that's defined by x, y, that is, right? X goes from A to B and Y goes from C to D, so I'm really just building a rectangle here. A to B, C to D, right? Just like we've been doing. What I'm saying is, if we have this region, all things considered, this integral, double integral over the area, over the region, fact the same. Remember when I was doing that other question, I said, hey, do you guys want to integrate with y or x first? And you chose x, because you were thinking of it as slicing it up into a grid. And it doesn't matter if you sit down and slice that grid y first, and then go back and slice it horizontally. It doesn't matter which way you do your slicing. You could slice vertically first and then horizontally, or vice versa. So Fubini's theorem is literally saying, hey, you pick. The advantage of this is that you guys know these integrals can get out of control really fast. So it can be advantageous to pick the correct one so that the integral doesn't grow very quickly. It can also be advantageous to do because we're going to get to these regions that aren't rectangular, in which case picking these bounds becomes more complicated. What I want you to think of here is that this is the same thing that you did. Again, I'm going to keep drawing parallels to your previous calculus knowledge. When you were taking your original calc class, you said, oh, how do I find the area between these two curves? And you said, oh, I can integrate with respect to x. Or, and then it was a nice day when you found out that you'd have to do this for certain curves and polar coordinate things. You said, oh, I can integrate with respect to y. You guys remember doing that? And you got to pick which way you wanted to slice this. It's the same thing happening here. Pick which way you want to slice first. It can be advantageous to pick either direction. To prove that, unless I've got my notes backwards, yeah, we're going to redo example 2. Did we do dy dx the first time? Yeah. No, we did dx dy. So now we're going to do dy dx. We do have a quiz today.
You got your book. We do.
Mm-hmm.
You got your book too.
So this is going to be the same thing if we end up integrating with respect to y first. So I integrate with respect to y. Holding x constant, nothing shocking there. I'm going to go through now, I evaluate this. Again, when I plug in 0, everything disappears. So this is the same as just assuming I was going to plug in 2. Now I'm ready to integrate with respect to x. You notice you're seeing a lot of the same numbers repeat.
So if the lower bound wasn't 0, will we ever have to find that c constant when we take an integral or something? Or that c constant? Will we ever have to find that using this method? Just so I can prepare myself.
I guess I don't recall which C you're talking about.
It's for
This
indefinite
is, yeah,
intervals.
this is what a definite interval is.
Oh, you're thinking about the plus a constant at the end when we get done integrating.
Right.
So
That's different to this.
no, it's not any different than this. That's still operating in the background. So right here, when I go to evaluate from 0 to 2, right, this would look like 16 times 2 minus x squared times 2 minus 2 cubed over 2 plus a constant. minus 16 times 0 minus x squared times 0 minus 2, 0 cubed over 2 plus a constant. Because it's a definite integral, this plus c and this plus c will cancel out every time. So while you may have been taught initially that if it's a definite integral, you don't need to include the constant, if you do include the plus c when you do your integration, it'll work out just fine, it'll go away.
And that's only because the lower bound is 0, but what if the lower bound is for 1? With that,
It doesn't matter if it doesn't matter what the lower bound is, right?
Right.
If I change this to 18, or say 10, so I can do it real fast, and this is 20, this is still plus c, this is still plus c, they still go away. You're thinking it will change the value of the c if I was solving for it, but in this case, since it's a definite integral, it's always going to go away. Should get 48 again, punch this in your calculator. So the direction, the order in which I decided to slice this grid plays no role in what answer you get. And again, that's just because we can slice it either way first, right? And in fact, when you guys were giving me the answers for the snow thing, you said, oh, remember I had different numbers for the snow inches? You said, oh, he started at the top of the picture. That's why. I accidentally started in the opposite direction than you guys did, because I was reading left to right, top to bottom, because I had it on a piece of paper, whereas on the board I'm so short I had to point at the lowest one and work up. What?
I said you hate for cumulativeness.
So, yeah, and that's exactly what's happening here, right? So, let's take a look at example 3. Now, example 3 has a slight typo in it. But here's what's happening. So we run apparently a fence company. So our fence company, when we sell fences, right, we make money off of it, but it costs us money to make these fence posts. So if you've ever studied business, what you'll know is that there comes a certain point, right, I have to sell so many fences before I start making a profit, because I got to pay my workers, I got to buy the electricity, I've got to do all these things. There also comes a certain point, so I've got to make so many fences just to break even. After that, each one's profit. There also comes a point, however, in business where I'm selling too many fences for the infrastructure I have. Right? My factory's at maximum output, but they still want more fences, so I start paying everyone overtime. Well, paying everyone overtime is making me lose money, so I need to stop making fences. So what's happening here is this PXY is giving the profit in thousands of dollars per fence section at the time based on, it's giving the profit margin per fence post that you're making. Right? So if you tell this function, okay, 2 months from now, if you're making 18 fence sections, what kind of profit are you turning? That's what it's saying. It's the profit per fence section. So what I want to know then is I'm going to integrate, do the double integral of this profit function. So here is the setup. I want you guys to give a shot at doing this double integral, and then we'll talk about this interpretation together. What is this trying to get across to us? So see if you can calculate the double integral. I'll walk around and help as you guys do this. And we'll work on this interpretation.